Okay, so I'll start the discussion session 8. Uh, so in the last session, we started fuzzy logic, right? We started discussing the second part of the course, which is fuzzy logic. And we talked about what logic broadly means. And we had a discussion on classical logic as well. More specifically, we talked about propositional logic and first order logic. And therein, we talked about tautology and contradictions. These are propositions that are always true and always false. And then we also talked a little bit about logical implication. And we then talked about how natural language statements can be translated into propositional or first order logic. And we also talked about something called as Liar's paradox, and that uh, suggested that classical logic, which essentially is logic based on two truth values, 0 and 1, is not adequate. So we found a motivation for having systems of logic wherein you have more than two truth values or so-called multi-valued logics. And then we talked about a specific type of multi-valued logic, namely Lukasiewicz logic, LN. And then we also uh, talked about L infinity, which is the logic of Lukasiewicz and Tarski. And in this particular logic, the entire unit interval was the set of truth values, right? And we talked, I argued that this is a type of fuzzy logic, right? Because here the set of truth values is the entire unit interval. Okay. Now, we will now talk about inferences in classical logic, right? So, in last session, we talked about how to, given propositions P and Q or atomic propositions P and Q, we can form more complex propositions. And we talked about how we can compute their truth values when we know the truth values of individual propositions, right? But as I declared in the beginning of last session, that in logic, we are interested in correct ways of making inference, right? And inference essentially is the process of arriving at a particular conclusion given one or more premises, right? So in this class, we'll study uh, what are the correct ways of making inferences, right? Now, in classical logic, we have three fundamental principles of inference, and they are called as modus ponens, modus tollens, and hypothetical syllogism. And we'll go through these three principles one by one and try to understand what they mean. And we will also extend them to the fuzzy setting, right? So these principles of inference hold in classical logic. They're formulated in classical logic, but we can extend them into fuzzy setting as well. Now, we won't do that in this particular session because that's the subject for next week, but we will definitely understand what these inference rules are, inference principles are in the classical setting. So let us start with modus ponens. So this word modus I'll be using again and again, so it is useful to understand what it means. So modus is essentially Latin for way or method or mode, right? And ponens comes from a Latin word ponia, which means to affirm or to set down or to place, right? So putting these two together, modus ponens essentially means the way to affirm something, the way that affirms or the affirming mode. So more specifically, what I mean by that is given an implication P imply Q, or if P then Q, and proposition P, you can infer Q, right? So we performed an inference, right? We reached the conclusion Q using the set of these two premises. So this is what is called as modus ponens. So this way of doing inference essentially affirms P, right? And then it helps us conclude Q. In other words, what we are saying is if P then Q and P, then Q. That is, if we know that if P then Q holds, and we know that P holds, then we can conclude Q holds. Or in other words, when we write this in logic, this is what it means. This is what modus ponens means. That if P imply Q holds and P holds, then that logically implies Q. In other words, for any propositions P and Q is a tautology. So regardless of what P and Q are, they can have any truth values, they could be any propositions. This statement is a tautology, which means that if you know that P imply Q holds and P holds, then you can always infer Q. Okay. So let us convince ourselves that this is indeed a tautology, right? And we know how to do that. We'll just draw the truth table of this particular expression. Okay. So before doing that, it's useful to take an example to understand what modus ponens is. And this kind of reasoning is something that we do every day, right, in our day-to-day language. For example, it's not unusual to think that if it is raining, then the streets are wet, right? So this P imply Q holds. So this is basically P and this is Q. And this again is P. So we know that if it is raining, then the streets are wet. This P imply Q holds. And further, if we know that it is raining, suppose it is raining today in Delhi, then we can conclude the streets are wet, right? So this modus ponens is not something very new. It's a kind of reasoning that we have been doing for a long time in our day-to-day lives, right? So this is an example of inference that is modus ponens. So let us see if this is indeed a tautology. In other words, let us see if this modus ponens, this way of doing inference is actually valid. So in order to do that, we will draw the truth table of this particular expression, right? And in order to do that, we first list out the possible truth value assignments for propositions P and Q. And we know that the truth table of P imply Q look like this. So it is 1 in all the cases except when P is true and Q is false. So we have this basically truth table for P imply Q. Now let us draw the truth table of P imply Q and P. So we are focusing on first column and the third column. And we are doing this conjunction and. So this is 0, this is 0, this is 0, and this is 1. And now let us finally draw the truth table of this expression. So we have this fourth column implying Q, which is the second column. So 0 implies 0 is 1. This again is 1. This again is 1. This again is 1. So in other words, this expression P imply Q and P implying Q is true, always true. Or in other words, it's a tautology, which means that no matter what P and Q are, if you know that P imply Q and P, then you can always infer Q. Okay. So this is what modus ponens is. Now, the other way of making inference, the other inference principle in classical logic is called as modus tollens. So tollens comes from the Latin tollere, which means to deny, right? Or to take away. So the literal meaning of modus tollens is that the way that denies or the denying mode. Concretely, what it means is, okay, so I think there is a typo in the slide. Anyways, so maybe I'll just edit this. Sorry for the typo. Okay. Should have known this. Okay. So what modus tollens tells us is that if we know that P imply Q and we know that not Q holds, that is Q is not true, then we can infer that not P is true, or in other words, P is false, right? So if we translate this into logic, it essentially means that if P imply Q and not Q implies not P, right? So if we know that P imply Q holds, and we further know that Q does not hold, that is, Q is false, or in other words, not Q is true, then we can always infer not P, or in other words, we can always infer that P is not true. And this is not difficult to think about, right? Because if these two conditions hold, then P has to be false. Because if P were to be true, then Q would have, then through the first statement, we would infer that Q would be true. But we already know that Q is false. So therefore, P must have been false to begin with. Or in other words, not P would have been true, right? So this is what is called as modus tollens. So to take an example, to ignore these typos, suppose I have a implication that if the dog barks, then a stranger is at the door, right? So what this means is that if the dog barks, then we know for a fact that there is a stranger at the door. Now, if we know that there is no stranger at the door, or in other words, so this is P and this is Q, right? And this basically is not Q. So, or you can use this symbol as well, whatever you like, right? So we have P imply Q, where P is if the dog barks, and Q is there is a stranger at the door. And we further have not Q, which is there is no stranger at the door. Then what would be the conclusion? The conclusion will be not P. In other words, the dog did not bark, right? And it's of course obvious intuitively, because if the dog indeed barked, then that would have meant that there is a stranger at the door. But we already know that there is no stranger at the door, which means that the dog must should not did not bark, right? So this kind of reasoning is something that we do on a day-to-day basis, right? And we are essentially codifying those uh, these way of reasoning that we do on a day-to-day basis, right? So a lot of the study of logic, in a sense, started with this desire that we think in certain ways, right? We reason in certain ways, and we want to codify it, we want to formalize it, so that we can better understand how we think, right? Or how we argue or how we reason. So, modus tollens, this phrase, you may have heard it for the first time, but the essence of this inference principle is something that you all are familiar with. In fact, we have been doing it for a long time. Okay. Now uh, let us check if this. There is a lot of typos. So just ignore the first part of the slide. So we are interested in checking if modus tollens is actually valid, whether it is formally valid, or in other words, we are interested in checking if this is a tautology, right? Because precisely is what modus tollens tells us, right? That if P imply Q holds and not P holds, then not Q holds, then that necessarily means that not P holds, right? And we want to check if if this is indeed a tautology. In other words, we want to check if modus tollens is actually valid. So we will do that. So in order to do that, we'll draw the truth table of this complicated expression. So towards that, we first list out the truth values of P and Q, all the possible truth values for P and Q, and then we draw the truth table of P imply Q. Now we'll draw the truth table of not Q and not P. So that would be 1, 0, 1, 0, and these two would be 1, 1, and 0, 0. Right? Now let us compute the truth value of P imply Q and not Q. So we'll focus on the third column and the fourth column. So this will be 1, this will be 1, this will be 0, this will be 0. Now let us compute the truth values of this complicated expression. So we'll focus on the fourth column and the fifth column, sixth column, and the fifth column. So 1 imply 1 is 1, 1 imply 1 is again 1, 0 implies 0 is again 1, 0 implies 0 is again 1. So in other words, this expression, this formula, P imply Q and not Q imply not P is always true. It's a tautology, which means that regardless of the truth values of P and Q, regardless of what P and Q are, this formula, this way of inference, P imply Q and not Q implying not P always hold. So it holds irrespective of what P and Q are and what their truth values are. So in other words, this is basically this indicates that modus tollens is a valid inference principle. Okay. And finally, we have something called as hypothetical syllogism. Again, a new term, but I'm sure that you all are already familiar with it, right? So, hypothetical essentially meaning it comes from a Greek word that means conditional, right? So, in fact, hypothetical is a word that we often use in our day-to-day conversation. So, hypothetical is related to hypothesis, meaning essentially conditional, that you are talking about a particular condition. And syllogism, it's again comes from a Greek word, and it more or less means inference, right? The process of drawing a conclusion given a set of premises, right? So what hypothetical syllogism literally means is it's a reasoning using conditional statements, right? It's a reasoning together of conditional statements. So more specifically, what hypothetical syllogism tells you is that if you know that P imply Q for propositions P, Q, and R, if you know that P imply Q and you know Q imply R, then you can infer R. So basically, if you know that P imply Q holds, and if you know that Q imply R holds, and if you know that P holds, then you can infer R, right? And it should not be very difficult to see why, because we know or we already know that P and P imply Q already tells us Q, right? And if we know Q and we already know that Q imply R holds, so therefore R must hold as well, right? So in a sense, this is a kind of a transitivity, right? You know P imply Q and Q imply R, and you further know P, then you can easily infer R, right? So if you translate this logically, then this is what you get. So P and P imply Q and Q imply R tells you R. So again, we can draw the truth table of this like big expression to see if hypothetical syllogism formally holds. And I encourage you to do that. So take this as a homework. Again, so basically we have to draw the truth table of this big expression. So you start by listing all the possible truth value assignments of P, Q, and R. So we have three propositions, P, Q, and R, and each of those three propositions can take the truth value 0 or 1. So you have 8 possible cases, list them down, and then start by drawing the truth table of P imply Q and Q imply R, and then their conjunction, and then take its conjunction with P and see if this entire thing is always true or not. Okay, so take this as an exercise. I mean, you have already done in it in we have already uh, seen how to draw these truth tables in the last discussion session, so I don't want to repeat all that. But the point is that in classical logic, you have three ways of making inferences. You have modus ponens, modus tollens, and hypothetical syllogism. Modus ponens tells you that if P then Q and P holds, then you can infer Q. Modus tollens tells you that if P then Q holds and not Q holds, then you can infer not P. And hypothetical syllogism tells you that if you know that if P then Q, and you know if Q then P, if Q then R, and you know P, then you can infer R, right? So essentially, it's a two-step inference, right? And what is to be noted, and it is something, and this is something that I've already emphasized, that these ways of making inferences are valid irrespective of what propositions P, Q, and R are, regardless of what P, Q, and R stand for and what are their truth values. It doesn't matter. These principles of inference always hold, right? And this is basically what we are establishing by drawing these truth tables, right? So, for example, uh, this is modus ponens, right? And then we drew its truth table, and it turned out that this is a tautology, which means that logically implies Q. So this holds regardless of what P, Q, and PQ are and what are their truth values. This is always going to hold. So the point that you must keep in mind is that these inference rules or this inference principles, these principles of inference hold regardless of the content of the propositions P, Q, and R. Their validity actually follows from the logical form, follows from how the connectives and or and not behave. So the validity of these three inference rules are an artifact of how classical logic behaves, right? And they are entirely independent of what P, Q, and R are, right? So, this is something that you must recognize that these inference principles they have worked because they are independent of what we are talking about. P and Q could be anything, but as long as we know that if P then Q and P holds, then we can always infer Q. So in other words, this is sort of an abstract analysis. We are doing an abstract argument. We are making an abstract argument. Uh, P, Q, and R could be anything, and we can always infer Q if we know P, then Q and P. Anyway, so I don't want to belabor the point. This is something that you must keep in mind. Now, so we talked about these three inference principles, right? And these inference principles are exact in nature. And what do I mean by that? It means that if we have a rule, P imply Q, then in order to make an inference, we either need to know P, in which ways we can infer Q using modus ponens, or we need to know not Q, in which case we can infer not P using modus tollens. So in other words, that if we have a rule P imply Q, then in order to make an inference using this classical principles of inference, we need to know the exact P or not Q. So in other words, let us take a more practical example. Suppose f is a function from R to R, then we know that mm, f is differentiable implies f is continuous, right? It's well known. But suppose we have a function f that is differentiable at all x except 0, 1, right? So this, in our case, this is proposition P and this is proposition Q. And now we have a new proposition P dash. Now, P dash and P are similar in a sense that they both talk about differentiability, but they're not same, right? PDAS states that f is differentiable at all real numbers except two real numbers, right? Now, if we use classical logic, then we cannot infer that f is continuous, right? Because for us to infer q, we must have p, and in this case, we don't have p, right? We need exact p in order to infer q. Here, p dash we have p dash, and p dash is not p. Although I think you all would agree that p dash is somewhat similar to p, right? Because both of them talks about differentiability. But as far as classical logic is concerned, we cannot make any inference because inference in classical logic is exact in nature. To be able to infer anything from p imply q, we must know either p or we must know either not q, right? But a major chunk of real life of reasoning that we do in real life is approximate in nature, right? For example, when we go to market, we often use this. We often reason as follows: that if tomato is fairly red, then it can be bought, right? And this is just an example. More, just think for yourself. We make inferences every day, all the time, and most of these inferences are approximate in nature rather than being exact. If we see a car coming towards us, we'll probably take side, right? Now, again, it's an example of approximate reasoning. It The velocity of the car plays a role in here. If a fast car is approaching towards us, we'll probably shift the lane, right? But if a car is really far apart, then we won't take any action. So the point is that the reasoning that we do in real life, a majority of real life reasoning is approximate in nature rather than being exact. And therefore, classical inference schemes, inference principles, inference rules, whatever you want to call them, like modus ponens or modus tollens or hypothetical syllogism, cannot work here because those principles allow us to do exact reasoning. While in real life, we do a lot of approximate reasoning, right? So there is a natural motivation to develop mathematics of approximate reasoning, right? We want to able to come up with a framework in which we can give some kind of mathematical meaning to this kind of reasoning. If tomato is fairly red, then it can be bought, right? So we want to develop a system, we develop a theory, mathematical theory in which such statements of approximate reasoning can be made some sense of. Okay, and this is where fuzzy set theory and fuzzy logic comes comes to rescue, right? So one of the most successful application of fuzzy set theory and fuzzy logic is in this area of approximate reasoning, right? The kind of reasoning that we do in our day-to-day lives. And by approximate reasoning, just to sort of give a more technical description of approximate reasoning, it refers to any way, any method or methodology that help us obtain meaningful outputs using imprecise rules and imprecise premises. In this particular case, if tomato is fairly red, now fairly red, what exactly fairly red means? It's an imprecise concept. The concept of color red is not precise. We don't really know at what point a color stops being red and becomes, I don't know, yellow, for example, right? So red as a concept is imprecise. It's a vague concept. Similarly, when you apply this word fairly to it, again, the imprecision remains, right? So in this particular statement, you have an imprecise premise, and from there you are deriving a conclusion regarding whether the tomato can be bought or not, right? So this is what approximate reasoning means. Approximate reasoning refers to methods using which we obtain some kind of meaningful output when we are dealing with imprecise premises and rules. Okay, so I hope I gave you a sense of why uh, approximate reasoning is important, right? So we started with classical logic and we then talked about inference rules in classical logic. We talked about these three rules: modus ponens, modus tollens, and hypothetical syllogism. And then we observed that these inferences are exact in nature. But in real life, we do approximate reasoning all the times. And therefore, there's a natural motivation to develop a mathematical theory for approximate reasoning. And this is where fuzzy set theory and fuzzy logic help us, right? So there are four important uh, pillars of approximate reasoning done using fuzzy set theory and fuzzy logic. First one is fuzzy propositions. Second one is truth values and linguistic hedges. The third one is fuzzy if-then rules, and the fourth one is the fuzzy inference schemes. So these are fuzzy counterparts of modus ponens and modus tollens and so on. Now, in this particular discussion session, we will just talk about fuzzy propositions, and we'll also talk about truth qualifiers and linguistic hedges, because this is basically the subject of this week's content. Uh, you will study about fuzzy if-then rules and fuzzy inference schemes in the next week, in the upcoming week. So we'll focus on fuzzy propositions and truth qualifiers and linguistic hedges. We'll try to understand what these terms mean. So let us start with fuzzy propositions. So proposition is something that I have described in the last session, right? A proposition is essentially a statement, a declarative statement, a declarative statement meaning that it is a statement. It is a sentence that tells you something about the world. It asserts something about the world. It declares something instead of asking something, right? So, is New Delhi capital of Delhi? It's not a declarative statement, right? Because it asks a question. On the other hand, if I say that New Delhi is located in Delhi, it's an example of a declarative statement. In other words, it's a proposition because it tells you something. It declares something about the world. Anyways, so a classical proposition or a proposition in classical logic is assigned a truth value of 1 or a truth value of 0. 1 meaning exactly true or 0 meaning exactly false. Now, a fuzzy proposition, on the other hand, is again, it's a proposition, it's a declarative statement whose truth value is a matter of degree rather than just being completely true or completely false. The truth value of a fuzzy proposition is expressed by some number in the unit interval, right? So, Delhi is warm today. This statement uh, is a fuzzy proposition, right? Because for the truth of this particular statement, Delhi is warm is a matter of degree, right? So I would say that it's true to degree point 0.8, but someone can say that it's true to degree point 0.6 and so on. But the point is that this statement, this proposition, Delhi is warm today, is much more meaningfully captured by assigning a truth value that lies in the unit interval rather than saying that it is completely true or completely false. So such statements are example of fuzzy propositions, right? So the thing to be remembered is that fuzzy propositions are statements. These are propositions for which the truth value is a matter of degree, right? And that is expressed using a number in the unit interval. So a couple of more examples. Fatima is tall. Again, it's a fuzzy proposition, right? Because uh, I think everyone would argue that this statement can be more meaningfully modeled by assigning it truth values between 0 and 1 rather than simply assigning a degree truth value 0, truth value 1, right? So if Fatima is 5.8, then probably she is tall to degree 1. But if she is 4'11, then if she is say 5'5", 5'5" inch tall, then she is probably tall to degree point 0.8, right? So similarly, the shirt is very yellow. It's again an example of a fuzzy proposition, right? Because we are talking about the color of the shirt. Specifically, we are talking about color yellow of the shirt. And color yellow is a vague concept. We don't really know at what point a color starts being yellow or stops being yellow. So assigning it a truth value of 0 and 1 does not make a whole lot of sense, right? It's much more meaningful to uh, assign this particular statement a truth value between 0 and 1 instead just 0 or instead of one, or just one. Okay. Now, fuzzy propositions are of four types: uh, unconditional and unqualified, unconditional and qualified, conditional and unqualified, and the finally conditional and qualified. Now, what conditional and qualified mean, we'll soon understand. But thing to remember is that fuzzy propositions, the collection of fuzzy propositions, is divided into these four broad classes. So let us start with the first type: unconditional and unqualified fuzzy propositions. So these are fuzzy propositions that just express some property of some object. They are not of the form if then, and they don't involve something called as truth qualifiers. We will soon see what these truth qualifiers are. But just to describe unconditional and unqualified fuzzy propositions, these propositions are essentially statements that express some property of some object. In this sentence, the first sentence, Fatima is tall. So we are describing a particular property of being tall in this case, of a certain object. In that case, in this particular case, the object happens to be a human being named Fatima. In second case, the room is warm. Again, this is a statement that expresses a fuzzy property, namely the property of being warm of a particular object, a room, right? So the canonical form of such propositions is this: V is F. In the first case, V is Fatima. Uh, okay, so maybe I'll first describe what these V and F are, and then we'll try to model statements like this uh, using this form. So the canonical form of such propositions of unconditional and unqualified fuzzy propositions is V is F. So V is some variable that assume value in a universal set capital V, and F is a fuzzy set over V, this universe, F, expressing some fuzzy property basically. So in first case, Fatima is tall. This F should express the fuzzy predicate tall, and V is basically the height of Fatima. So to summarize, unconditional and unqualified fuzzy propositions are those fuzzy propositions that expresses some fuzzy property, some fuzzy predicate, some fuzzy whatever you want to call it, quality of a particular object, right? And the standard form of such propositions is like this: V is F, where V is some variable that take values in universal set capital V, and F is some fuzzy set over V. And this fuzzy set essentially expresses some fuzzy predicate. Okay, so let us try to make this a bit concrete. So consider this proposition for Fatima is tall, right? And the canonical form of a proposition of this type is V is F. So here V, the variable V, would be height of Fatima. The set V, the universe capital V, would be the set of all possible human heights. So from 50 centimeter to say 210 centimeter. And tall would be a fuzzy set over V, right? So this fuzzy set would describe to what degree different human heights are to be considered tall. So tall 180 centimeter would probably be zero point 0.9. Tall 145 centimeter would probably 0.2. Again, you can construct the appropriate fuzzy set to capture the concept of tall height, but the idea is that a unconditional, unqualified fuzzy proposition is of this form, right? Where V is a variable that take values in some some universal set, capital V, and F is a fuzzy set over that particular universe, right? And it captures some vague concept, some fuzzy predicate. In this case, that vague concept or that fuzzy predicate is tall, right? Now, the question is, given a unconditional and unqualified fuzzy proposition, how do we compute its truth value? Right? Because ultimately we are in the business of finding out to what extent a fuzzy proposition is true, right? So it makes sense to ask this question. How do we find out the truth value of unconditional and unqualified fuzzy propositions? And we do this in the following way. So this is the standard form of a fuzzy proposition, unconditional and unqualified fuzzy proposition. Now, if we know that the variable v takes a particular value, small v, in the universe, then the truth value of the proposition is given by the value of the fuzzy set at that particular value. So to take this particular example, if we know the height of Fatima is h, then the truth value of this proposition p, which we denote by t of p, is the membership function of concept tall at height h, right? So I'm using, you can use the more familiar notation, right? So Fatima is tall is a fuzzy proposition. It's an unconditional, unqualified fuzzy proposition. And we formalize it like this. So V is a variable that essentially corresponds to height of Fatima. V is the set of all possible human heights. And then tall is a fuzzy set over this set of possible human heights that captures the vague concept of being tall. And then given a particular height h, the truth value of this proposition P is evaluated like this. So you simply evaluate the membership function of tall at h, and that would give you the truth value of this particular fuzzy proposition. Okay, so let us take another example. Here we have a fuzzy proposition, the room is warm. This again is unconditional and unqualified. Why unconditional? Because it is not of the form if P then Q, right? And why unqualified? Because here we don't have any truth qualifier. Now we will this notion of unconditional would become much more clearer to you when I talk about conditional statements, a conditional proposition. But a good rule of thumb for identifying if a fuzzy proposition is unconditional or not is to see if it has if and then in it. And this is unqualified. The room is warm is unqualified because there is no truth qualifier. Again, we will soon study what truth qualifiers are. So basically, these are terms like very true, fairly false, and so on. But here we don't have any such thing. We just have a statement that expresses some fuzzy property, some fuzzy predicate, some vague concept about some object. So warm is the fuzzy predicate and room is the object. So this is an example of unconditional and unqualified fuzzy proposition. Now here the variable V would be the temperature of the room, and this variable would take value in the universal set V, and V would essentially be the set of all possible human temperatures, set of all possible room temperature, right? So from minus 50 to 50 degrees centigrade, for example, right? You can say that minus a much more appropriate universe would be minus 20 to 50 degrees centigrade. But again, that is something that we have freedom to decide. Anyways, and warm would be a fuzzy set over this universe of possible room temperature. And this fuzzy set would describe to what extent different possible room temperatures are warm. So 35 degrees centigrade would definitely be warm to degree 1, but a temperature of say 5 degrees centigrade is 15 degrees centigrade is probably warm to extent point 0.1 or degree point 0.1, right? Okay. Now, suppose I know that the room temperature is T. Suppose I know that the temperature is T, then the truth value of this proposition P, that is TP, would essentially be warm of T, or in other words, it would be the value of the membership function of fuzzy set warm at T, right? So just to summarize what we have done so far, we talked about fuzzy propositions. So these are propositions that are these propositions are those kind of propositions that take value whose truth value is some number in the unit interval, right? As opposed to classical propositions where truth value is either zero or either one. Then we discussed that there are four kinds of fuzzy propositions. First one is unconditional and unqualified fuzzy propositions. These are propositions that expresses some fuzzy predicate about an object. And the standard form of such statement is V is F, where V is some variable that take values in a universal set capital V, and F is a fuzzy set over that universe capital V. And this is how we compute the truth value of such propositions. Now let us look at this second type of fuzzy proposition. So these are conditional and unqualified. So conditional means that you'll have a if-then statement. So if you take the first example, if temperature is high, then motor speed is high. So conditional meaning you'll have if and then. Similarly, the second example, if the tomato is red, then it is ripe. So the presence of if as well as then indicates that it's a conditional fuzzy proposition, and it still is unqualified because we don't have any truth qualifier here. We don't have is very true. For example, we don't have a statement like if the tomato is red, then it is ripe is very true, right? So conditional because we have if and then, and unqualified because we don't have any truth qualifiers in in these two propositions. Okay. So the standard form, the canonical form of such proposition is like this. If X is A, then Y is B. A if then statement basically, right? So again, X and Y are variables that assume value in universal sets capital X and capital Y. And A and B are fuzzy sets over X and Y respectively. Okay. So to take an example, so let us consider the first sentence, the first proposition. If temperature is high, then motor speed is high. So here X, the variable X denotes the temperature and the variable Y denotes the motor speed. And they take values in capital X and capital Y. So X is denoting temperature. So an appropriate universe for this variable would be minus 20 to 50 degrees centigrade. Y denotes the motor speed. So an appropriate universe Y, capital Y would be 0 to 100,000 RPM, right? And A and B are fuzzy set. A is a fuzzy set over X, the set of possible temperatures, expressing the wake concept high temperature, right? Because if temperature is high, so this high essentially corresponds to high temperature, and that is captured using a fuzzy set A over X. And similarly, B here is a fuzzy set over Y that expresses the wake concept high speed. So then motor speed is high. High here means high motor speed, right? Or high speed, in other words. So in this particular conditional and unqualified fuzzy proposition, the variable X denotes the temperature, variable Y denotes the motor speed, and they take values in the appropriate universe, capital X and capital Y. And A is a fuzzy set that captures the concept of high temperature, and it is a fuzzy set over X. And B is a fuzzy set over Y, and it captures the concept of the fuzzy concept or wake concept, whatever you want to call it, of high speed. Okay. Now, so now that we understand what is the standard form of conditional and unqualified fuzzy propositions, it is natural to ask how do we compute its truth value? If I have a a fuzzy proposition of this form, how do I compute its truth value? Now, we begin by noticing that this proposition P expresses some kind of conditionality, right? Conditionality of variable y on variable x. If temperature is high, then motor speed is high. So there is a conditionality of motor speed in terms of the temperature, right? So the proposition P expresses some kind of conditionality, and this conditionality is captured using a fuzzy implication, right? And the proposition P and the truth value of proposition P is modeled by a fuzzy relation from x to y, and this fuzzy relation is built using a fuzzy implication. Okay, so a conditional fuzzy proposition expresses some kind of conditionality. We need to capture that conditionality. We do that using a fuzzy implication, and using that fuzzy implication, we then find out the truth value of this proposition P. Okay, so I'll make this idea more concrete. But before that, we need to discuss what a fuzzy implication is, right? We know that what T norms and what P conorms are. We also know what fuzzy negations are, right? And these operations are precisely the fuzzy counterparts of classical connectives. So T norms are basically fuzzy and T conorms are fuzzy or. Similarly, fuzzy negations are fuzzy counterparts of classical negation. So in a similar manner, fuzzy implication is the fuzzy counterpart of the classical implication, right? And it can be defined axiomatically as well, right? So we defined T-norms axiomatically. It's an operation from 0, comma 1 cross 0, comma 1 to 0, comma 1 that satisfied certain properties. So for example, commutativity, associativity, and so on. In a similar manner, you can define fuzzy implications. So a fuzzy implication, I, is a map from 0, comma 1 cross 0, comma 1 to 0, comma 1 that is decreasing in the first variable. It is increasing in the second variable. So decreasing in first, increasing in second, and it satisfies these four boundary conditions. Now, if you notice that these boundary conditions are precisely the classical boundary conditions. So we know that we have already seen that if P and Q are classical propositions, that is, they take truth value 0 or 1, then this is how the truth table of P imply Q looks like, right? In other words, when P is both P and Q are true, then P imply Q is true. This is what this means. So I of 1 comma 1 is 1. It means when the first truth value and the second truth value are both 1, then the truth value basically of P imply Q is again 1. Similarly, the last, when the truth values of both P and Q are 0, then truth value of P imply Q is 1. So this is what this particular boundary condition expresses, that I of 0 comma 0 is 1. Similarly this, and similarly that, right? So in other words, a fuzzy implication is a map from 0 comma 1 cross 0 comma 1 to 0 comma 1, or in other words, from unit square to unit interval, that is decreasing in the first argument, increasing in the second argument, and satisfies the classical boundary condition. Okay. So two examples of fuzzy implications are ILK and IKD. So you should remember that this is precisely the Ukashevich implication that we talked about in the last discussion session. And this is basically KD stands for uh, Klein-Dinos. These were the people who proposed this implication, right? Now, fuzzy implication is the fuzzy counterpart of the classical implication. Okay. Now, if x is a, then y is p. We have a conditionality here of variable y on variable x. And to capture this conditionality, we use the fuzzy implication. We use a certain fuzzy implication. And using this fuzzy implication, we then model the truth value of P. How do we do that? We do it like this. We start with a fuzzy implication I, and then the truth value of this proposition P is modeled using a fuzzy relation R from X to Y. So the truth value of this proposition P is given by a fuzzy relation R, and this fuzzy relation R is a relation from X cross Y, right? And it is kind of like obvious, right? Because when we are talking about unconditional and unqualified fuzzy propositions, we had just one variable, right? And that variable can take a particular value, and that value determines the truth value of the proposition. But in conditional and unqualified fuzzy propositions, we have two variables, X and Y, right? And therefore, given a particular value for variable X and a particular value for variable Y, we'll have a particular truth value of proposition P, right? So there, this of course is a relation. We have two sets, X and Y, okay? And this is how the truth value, this is how this relation R is defined. So the value of relation R at X comma Y is you take the membership of X in A, membership of Y in B, and then you apply the implication I. And that would give you the membership of X comma Y in relation R. So the degree of relationship, the degree of conditionality between X and Y is computed in the following manner, in this particular manner. Okay. And therefore, given a particular value for variable X, say X naught, and variable Y, say Y naught, the truth value of this proposition, P, this particular proposition, is nothing but the membership of X naught comma Y naught in the relation R. Or in other words, it's basically this. Okay. So to summarize, the second type of fuzzy proposition we are discussing are unconditional and unqualified fuzzy propositions. So these are fuzzy propositions that are of the form if then. Basically, these are if then statements. And the standard form of such propositions is this. Now, here we have two variables, right? And given a specific value of those two variables, we want to compute the truth value of the entire proposition. We do that using the help of a fuzzy implication. The need for fuzzy implication is obvious because a if then statement expresses conditionality and we want to capture that conditionality. Just a minute. Sorry for the interruption. Okay. So, right. So there is a conditionality expressed by a conditional fuzzy proposition, and we capture that using uh, a relation, and that relation is built using a fuzzy implication, right? So this is how that fuzzy relation is defined. Now let us take a concrete example and see how this plays out. So let us start with this. If temperature is high, then motor speed is high. We already discussed in this particular proposition what the variables x, y, and fuzzy sets a and b are. Now suppose we know that the temperature is for 35 degrees centigrade and the motor speed is 500 rpm. Then what would be the truth value of the proposition P? It would be given like this, right? In other words, and this is basically how the relation R is defined. Okay. And if we use Ukashevich implication, then this would be right? And if you use KD implication, then this would be right. Okay, so I hope you got a sense of what conditional and unqualified fuzzy propositions are and how do we compute its truth value. Now, I also want to make a point about how we can efficiently compute this relation R. Uh, so when we talked about fuzzy relations, we talked about fuzzy relational composition as well. That given two fuzzy relations, how can we compose them? And there I talked about that there's this process of relational composition can be seen as a special type of matrix multiplication. So the ordinary matrix multiplication involves sum of products, right? And this the max-min composition of relation can be seen as max of min matrix multiplication, right? So a similar kind of intuition can be developed here as well, right? So instead of doing matrix multiplication, here we will do something called as an outer product. So I hope you are familiar with something called as dot product, or what is also called as an inner product. And then there is something called as an outer product. So this is something that you, I don't know, must have studied in linear algebra. So just to revise a dot product, if I take 1, 2, and 3, if I take two vectors in R3, then their inner product is obtained by multiplying the corresponding entries and then adding them up. So 1 multiplied by 2 is 2, plus 2 multiplied by 3 is 6, plus 3 multiplied by 5 is 15, right? So this would give you 23, right? Okay. And then we have something called as outer product as well. So in outer product, what we do is, so this inner product between x and y is essentially 1, 2, and 3 ma- ma- matrix multi. So these vectors can be seen as matrices, right? So these are essentially column matrices. And the dot product or the inner product of x and y is defined as the matrix multiplication between x transpose and y, right? Now the outer product between x and y, so let us denote it by x dot o, is given in this manner. In other words, it is x multiplied by y transpose. And instead of giving a particular number, it actually produces a matrix. So this is a 3 by 1 matrix. This is 1 by 3 matrix. So we'll end up getting a 3 by 3 matrix. And this would be what would be the first entry, the 1 comma 1th entry of this matrix. It would be 1 multiplied by 2. So 2. So I hope you know how to like do ordinary matrix multiplication. That's what I'm doing. And in this particular case, it would be these will be the entries, right? So what just did is recall the concept of inner product and outer product. Now this relation R can be seen as an outer product when your underlying universe X and Y are finite. So what do I mean by that? So let us take a specific case. Suppose that our X consists of three elements, X1, X2, X3, Y consists of two elements, Y1 and Y2, and the fuzzy sets A and B are given in this manner. And we consider the Ukashevich implication. So we know that the relation R which expresses the truth value of the proposition is defined in this manner, right? So if I want to say evaluate the uh, truth value of the proposition P when X is say X1 and Y is Y2, then that truth value would essentially be the membership of X1 comma Y2 in R. In other words, that would be mu a x1 comma mu b y2. This we know is zero point 0.3 and this we know is zero point 0.1. And when we use Ukashevich implication, we get 1 minus zero point 0.3 plus zero point 0.1. So this is 0.7, 0.8. So this entire thing would be 0.8. So the truth value of the proposition P when the variable x is x1 and variable y is equal to y2 is zero point 0.8, right? And suppose I want to compute the matrix R itself, right? So that we can easily figure out truth values whenever we are asked to compute one. Then what we will do is this. So R is outer product taken using implication I with B. So what do I mean by that? So A, which is a fuzzy set over the set capital X, which has three elements, can be seen as a column matrix, 0.3, 0.4, and 1. And B, which is a fuzzy set over universe Y, can be seen as a row matrix. And then we computed the outer product. So this is 3, 1, 1, 2, the resulting. And the way we compute the entries of this 3 by 2 matrix is by using the implication I. So the 1, 1th element would be obtained by looking at the first column of the first entry of A and the first entry of B. 0.3. Let us compute the 3, second entry. That is this particular entry. It would be evaluated using the third entry of matrix A and the second entry of matrix B. In other words, and similarly, you can compute everything. Right. So similar to how composition of fuzzy relations defined over finite universes can be seen as a special type of matrix multiplication, computing the fuzzy relation R, which expresses the truth value of some conditional and unqualified fuzzy proposition, can be seen as computing an outer product. And this outer product is based on a fuzzy implication. Okay. So this is basically what you get. So this is this way of remembering uh, computing R is kind of useful because it if a suppose X had 10 elements and Y had 5 elements, then individually listing down the elements, individually computing the truth values can be a tedious task, right? But if you look at from a matrix perspective, then things become somewhat easy. Okay, now let us do a problem. We have two universe, X and Y, and we have fuzzy set C1 and A2 over X, and we have fuzzy set B over Y. And we have a fuzzy proposition if A1 then B. And we have again a fuzzy proposition if A1 or A2 then B. Now you should be able to identify that this is a conditional fuzzy proposition because we have an if and we have a then. And moreover, this is unqualified because we don't have any truth qualifier. You know, this it does not say that if A1 then B, if A1 then B is very true or very false, so on and so forth. So we have conditional and unqualified fuzzy propositions. And we just saw how to compute the truth value of such propositions. And R1 and R2 denote the truth value of these propositions. So this is P1 and this is P2. And we are asked to compute mod of R1, mod of R2. So R1 is nothing but a relation, both R1 and in fact R2 are a fuzzy relation from X to Y. In other words, it's a fuzzy subset of X cross Y. And therefore, we can, of course, compute its scalar cardinality, basically the mod thing. So I hope you remember that the scalar cardinality of fuzzy set A over some universe X is denoted by this thing, and it is essentially obtained by adding all the membership values that A take. Okay. So we are required to compute the scalar cardinality of R1 and R2, and we are also asked if R1 and R2 are normal. So let us do this problem. So we'll first focus on P1. Now we know that R1 is a fuzzy set from X cross Y given by, and suppose that you are required to use the Kasevich implication. It's not specified in the question, but suppose that Lukasiewicz implication is to be used. Then this relation R1 would be given in this particular manner. Again, I'm just using the definitions, right? Now, fortunately, our underlying universe X and Y are finite. Therefore, you can do the outer product thing and can compute R1 in just one go. So let us do that. 0.3, 0.41. And we have to use Lukasiewicz implication. So we'll take the outer product with respect to Lukasiewicz implication. This would give us a 3 by 2 matrix. Okay. Now we just need to evaluate these numbers. So what would be the Lukasiewicz implication? So remember the Lukasiewicz implication is given by this formula. Right? Now we need to compute Lukasiewicz implication at 0.3, 0.7. So this would be 1 minus 0.3, giving us 0.7. 0.7 plus 0.7 plus 0.7 is 1.4. Minimum of 1 and 1.4 is again 1. Similarly, this. So 1 minus 0.3 is again 0.7, but 0.7 plus 0.1 is 0.8. So this would be 0.8. What would be 0.4, 0.7? So that would be 0.6 plus 0.7. So again, 1. This would be 0.6, 0.7. This would be 0.7. This would be 0.1. So in other words, R1 is 1, 1.7, 0.8, 0.7, 0.1. Now, is this calculation clear, by the way? Can someone unmute themselves, and is this calculation clear? How we are evaluating the relation R1, this R1 that expresses
Yes,
the truth
yes,
value?
sir.
Yes, sir. Able
Yes,
to
sir.
understand.
Okay. So we know the fuzzy relation R1. Now we need to compute the its cardinality, scalar cardinality. So we just need to add the all the membership values that R1 take. So 1.8 plus 1 plus 0.7, 0.7 plus 0.1. So you can easily evaluate that, right? So this is easy. Now, is R1 normal? Of course it is, because we see two ones here, right? Because the membership of x1 comma y1 in the relation R1 is 1, right? So R1 does attain the membership value 1, and therefore R1 is definitely normal. Now, and you can, of course, find mod of R1. Now, let us compute R2. Now, R2 is the fuzzy relation that expresses the truth value of fuzzy proposition F2. If A1 or A2, then B. Now, A1 or A2, we have two fuzzy sets A1 and A2 over universe X. And we need to model A1 or A2. How can we do that? Any suggestion? How can we do model A1 or A2? So we can simply take their union, right? So A1 union A2 is precisely A1 or A2. So or corresponds to union. In other words, suppose I define a new symbol A dash, and A dash stands for A1 or A2. A dash is going to be a fuzzy set over X, and the membership of A dash is going to be obtained by taking the union of A1 and A2, or in other words, it's A1 union A2. And since nothing is specified as to how this OR needs to be modeled, so we'll simply take the standard union. In other words, we'll take maximum. Okay. So if A1 or A2 then B is same as if A dash then B, and A dash is basically a fuzzy set over X that is given in this particular manner. So let us quickly evaluate A dash. So maximum of zero point 0.3 and 0.9, 0.9, maximum of 0.4 and 0.2, zero point 0.2, and maximum of 1 and 1, which is 1. And now we'll now compute the fuzzy relation R2, which is a fuzzy relation from X cross Y that captures the truth of proposition P2. And what is the formula? Right? This is how the fuzzy relation expressing the truth value of a conditional proposition is defined. But here the underlying universe are finite, and therefore we can use the outer product computation and can quickly compute R2. So R2 is basically will be obtained by computing the outer product of A dash and B. So A dash is 0.9, 0.4, and 1. We are taking outer product with Ukashevich-Tino, and then B. So B is 0.7 and 0.1. So at the end, we will get a 3 by 2 matrix. And again, I'm just performing the outer product, nothing more. Right? And we can now compute these individual values. So I'll compute this. 1 minus 0.9 is 0.1, so this is 0.8. 1 minus 0.0, so again this is 0.2. 0.6, this is 1 minus 0.6, 0.7, 0.7, and 0.1, right? So this is the relation R2, right? So this relation R2 expresses the truth value of proposition P2. So if we know that uh, x is so, by the way, this can be a point of confusion. I have not indicated the variable x and y here. I simply stated if A1 then B, and A1 and B are just fuzzy sets. So it uh, one may get confused, right? So this is just a shorthand for if x is A1, then y is B, where x and y are variables that take values in the set capital X and capital Y. But it's a common place to drop the symbol for variable, especially when, especially in questions where you're just required to compute R1 and R2, or the relations basically, right? So don't let this confuse you, right? So if it helps, write this properly, this proposition properly. If X is A1, then Y is B1, right? Anyways, so this is basically the relation R2, which means that if we know that X1 is X, the variable X is Y3 and the variable is Y2, then the truth value of proposition P2, which is nothing but the membership of X3 comma Y2 in relation R2, would be zero point 0.1. Okay. So again, this is R2. You can compute R2, mod of R2, the scalar cardinality of R2. All you need to do is add all these membership values. And it is easy to observe that this is definitely a normal fuzzy set because membership of x2 comma y1 in R2 is 1. So is R2 normal? Yes, it is. And you can compute mod of R1 and mod of R2. So I hope I gave you a sense of how uh, what unconditional and what conditional and unqualified truth propositions are, and how do we compute their truth values. Okay. Now we will discuss unconditional and qualified fuzzy propositions and conditional and qualified fuzzy propositions. Now, what qualified here means? It means that our fuzzy proposition involves a truth qualifier. And what is a truth qualifier? So these are words like very true, fairly false. So these are words that enable us to modify, or in other words, qualify fuzzy propositions so that more nuanced version of truth can be expressed. Simply saying that if tomato is ripe, then it can be bought is true. So it's just, just a normal fuzzy proposition. But saying that it is very true or it is fairly false, that if tomato is ripe, then it can be bought, enable us to express more refined version of truth, right? I hope you are able to get that. So adding very true or fairly false enable us to add an extra layer of nuance, right? So to go back to our familiar example, Fatima is tall is very true is an example of a qualified fuzzy proposition. And here the qualifier is very true. The room is warm is fairly false is an example of, again, a qualified fuzzy proposition. Here the qualifier is fairly true. Similarly, Amrit is young is absolutely true is again an example of a qualified fuzzy proposition. And here qualifier is absolutely true. Now, the question is, how do we mathematically model this truth qualifiers? So Jade, I hope you remember his name, he's the person who gave fuzzy sets. He proposed that this truth qualifiers can be modeled as fuzzy sets of unit interval. So that's quite a ingenious idea, right? So what do I mean by that? Suppose I have a proposition, a fuzzy proposition P, and we know that the truth value of P is zero point 0.8. Okay. So we have, suppose we have three situations. In first situation, the truth value is zero point 0.8, in second 0.9, in third 0.95. Now we are interested in investigating the truth value of P is very true. So P is some proposition, and then we qualified it by adding P is very true. Okay, and if it, let us use another symbol to denote this proposition. So P dash. So P dash is obtained by qualifying the proposition P using very true. Now, if P is 0.95, then it is very close to being absolutely true, right? In classical setting, we have the notion of exactly true and exactly false. Truth value zero, truth value one, and truth value zero. So if a proposition P is true to extent 0.95, then I think everyone would agree with me when I say that P is very true, is true to extent 1 or to degree 1. However, when P is the truth value of P is zero point 0.8, then the truth value of P dash, which is P is very true, is probably 0. 0.6, right? When P is true to degree zero point 0.9, or in other words, when truth value of proposition P is zero point 0.9, then the truth value of proposition P dash, which is P is very true, is probably zero point 0.8, right? So I hope you're able to recognize the underlying idea here. When you have a proposition P, and when you qualify it using the qualifier very true, then it modifies the truth values in such a manner that the truth values are modified in this manner. So 1.8.6. So if P is very true in the sense that if P, the truth value of P is very close to 1, then the truth value of P dash is also going to be close to 1. But if P has a truth value that is somewhat far away from 1, then P dash, which means that P is very true, would probably have a truth value that is smaller. So in other words, suppose 0, 1. On the horizontal axis, I am plotting the truth value of proposition P. On the vertical axis, I'm plotting the truth value of P dash. So if we did not have any truth qualifier, that is, if P dash were to be same as P, then this would have been the truth value of P dash. If P dash was, so this corresponds to the case when P dash is same as P. Now, let us consider the case when P dash is P is very true. Then in such a case, we'll have something like this, right? Because if P is very close to 1, if truth value of P is very close to 1, so say 0.95, then truth value of P dash is also close to 1. So, so sorry, this is zero point 0.9. So this is zero point 0.8. Similarly, when this is zero point 0.8, we have zero point 0.6. Okay. So this may take some time for you to truly understand this, but I hope I gave you a sense of why this makes sense. Whenever we add the qualifier very true, this is how the truth value of the proposition P changes. Okay. It so basically truth value of very true P, or in other words, P is very true, is obtained by squaring the truth value of P, right? Because if suppose P is true, the truth value of P is zero point 0.9, then the degree to which it is very true is going to be somewhat smaller than zero point 0.9, right? So maybe 0.81. And that can be obtained by taking the square of zero point 0.9, right? So typically The truth qualifier very true is modeled by this square function. In other words, if A is the truth value of some proposition P, then the truth value of P is very true is obtained by just squaring it. Similarly, fairly true. Fairly true means that even if a proposition is true to say extent point A, then it is fairly true to extent point one, to extent one. Because fairly true means that it's close to true. That's it. It need not be exactly true, just close to true. And therefore it can be modeled using this square root function. So if this is horizontal axis denotes the truth value of P, and vertical axis denotes the truth value of P is fairly true. So this is P dash. Now if P dash were to be same as P, we would get this straight line. Now we have fairly true. So we get this kind of U-shaped curve. So even if the truth value of P is point, say, 5, the truth value of P is fairly true would be uh, root point 0.5. Okay. So again, this can be slightly complicated at first, but take a moment to recognize that this is appropriate. These formulas make sense. We are starting with ordinary fuzzy propositions, and then we want to add a truth qualifier to it. And why do we want to do that? Because we want to express more nuanced versions of truth. And the question is, once we qualify a fuzzy proposition, how do I mathematically compute its truth value? And Jade gave this very clever idea that truth qualifiers themselves can be modeled as fuzzy sets of the unit interval, the set of truth values. And this is how those fuzzy, this uh, qualifiers are given. So look at first of all, look at now. Lastly, look at this absolutely true qualifier. Now, if someone is absolutely true, then that means its truth value is 1. In all the other cases, even if its truth value is 0.9, it would be absolutely true to degree 0. And this is basically what this formula expresses. A proposition is going to be absolutely true only when its truth value is going to be 1. In all the other cases, that is when the truth value is less than 1, the truth value of P is absolutely true is going to be 0. So take a moment to digest this. Take a moment to recognize that these are meaningful formulas. Okay. Now, having understood um, truth qualifiers, we are in a position to talk about unconditional and qualified fuzzy propositions. So these are propositions of this form. Fatima is tall is very true. The room is warm is fairly true. So we have an unconditional part, which means that there are no if and then. So we just have a statement that expresses some fuzzy property of some object. In this case, the property was tall and object was a human being named Fatima. And we had a truth qualifier, very true. Okay. So the canonical form, the standard form of propositions that are unconditional and qualified is V is F. So this is basically unconditional part, right? And then you have is S. So S is basically the truth qualifier here. So to uh, to be more specific, V is a variable that assume value in some universal set capital V. F is a fuzzy set over V that expresses some fuzzy predicate. This all we already talked about. And S is a truth qualifier, like very true, fairly false, absolutely true, so on and so forth. Right? Now the question is, how do I compute the truth value of such a statement? So I hope it is obvious that if we did not have this truth qualifier part, the truth value given a specific value of variable V would have been just f of V. Now that we have a truth qualifier S, we'll simply apply S to this f of V. and that would give you the truth value of the proposition P, an unconditional and qualified fuzzy proposition P. So to go back to our familiar example, Fatima is tall is very true. Our variable V would be the height of Fatima. The underlying universe capital V is going to be the set of all possible human heights. So 50 to 210 centimeter. Tall is going to be a fuzzy set over this set of possible human heights, expressing to what degree different height measurements correspond to the concept tall. And given a particular height h, the truth value of proposition P is tall h, and then you just apply the truth qualifier very true. In other words, tall h square. So if this notation is unfamiliar to you, then basically this is what we are doing. So we are computing the membership of height h in the fuzzy set tall height, and then we're taking it square. So I hope this made at least some sense to you, right? How exactly this truth qualifier is being modeled. Okay. Uh, was d- do you have any doubts, Jaya or Yugostina? You,
No, sir. No, sir.
okay, so I hope the idea was clear, right?
Yeah,
How
yeah.
truth value. Okay,
Yes, sir. Yes, sir.
sure. So we'll do one more question. Now we have a universe X that comprises of temperature measurements in of a room in degrees Celsius. So 0 degrees Celsius to 40 degrees Celsius is the universe X, and then we have a fuzzy set named comfortable that models the wake concept of comfortable temperature, and it is given by this triangular fuzzy set 16, 22, and 28. So I'll quickly draw this 16, 22, 28. And our universe is 0 all the way to 40. So this is our universe X, and this is our fuzzy set comfortable. So the equation of this line would be x minus 60 divided by 22 minus 16, which is 8. And this would be 28 minus 6 by 28 minus 6. So again, 6. Oh, sorry, this would be 6, right? 40. Okay. So this is how the membership function of the fuzzy set comfortable looks like. Our universe is from 0 to 40, and this is basically the shape of the membership function. And we have a proposition: a temperature of 19 degrees Celsius is very comfortable, is fairly true. So for a moment, forget this because I have not yet introduced the notion of uh, hedges. We will do that in a short while. So forget that there is a very here. So a temperature of 90 degrees centigrade is comfortable, is fairly true. Now, if we just focus on this part, it's a conditional and unqualified fuzzy proposition. It's a statement that talks about a fuzzy property, namely the property of being comfortable of a temperature of some object of of temperature. And then we have a truth qualifier. So we have a unconditional and qualified fuzzy proposition. So this is a unqualified, sorry. So this is a unconditional, my bad, unconditional and unqualified, qualified fuzzy proposition. Why unqualified? Because we don't have any if and then. And why qualified? Because we have a truth qualifier, fairly true, right? And we need to compute the truth value of this proposition. So what would be the truth value of this proposition? Suppose I denote it by T of P. Now here the variable, so here our variable V would be temperature measurement. and it is given that the underlying universe is X. So this variable V takes values in the universe X, which is the interval 0, 40. And the fuzzy predicate comfortable is captured by this fuzzy set. And we are given that this variable V takes the value 19 degrees centigrade, and we are required to compute the truth value of proposition P. So this would be, if this fairly true truth qualifier was not present, it would simply be comfortable 90. But since it is also there, so we'll also apply this fairly true, which I am abbreviating as FT, on this comfortable comma 90. Now, fairly true, we just saw, is modeled by this. So truth value ka square root. So we'll have square root of comfortable 90. And this would be, so 19 lies between 16 and 22. So this would be 19 minus 16 by 6. So you have 3 by 6 or 1 by 2, 1 by root 2. And I don't know what this turns out to be. Whatever. So maybe change the last option and say that it is 1 by 2. Right? So the point is that this is how the truth value of a unconditional and qualified fuzzy proposition is computed. Okay. Now, the last category is when you both have a conditionality and you have a qualification as well. So, namely, your proposition would look like this. If X is A, then Y is B. So, the conditional part, and then you have a truth qualifying part, which is S. And as usual, X and Y are variables that take values in some universal set X and universal set Y respectively. And A and B are fuzzy sets over these universes X and Y. And S is a truth qualifying. Now, the truth value, if this truth qualifier was not here, then the truth value of proposition P would have been evaluated using a fuzzy relation R, which is defined in this manner, right? But since we have a fuzzy truth qualifier S, what we will do is that we'll simply compute the truth value of this conditional part, and then we'll apply the truth qualifier S on it. So namely, this is basically what we do. Okay. And therefore, our relation R actually looks like this. You first compute the conditionality of variable Y on variable X, and then you apply the truth qualifier S on it. Okay. So the thing, basically, all you really need to remember is how do we evaluate the truth values of unconditional and unqualified fuzzy proposition. And that is very easy. You just compute the membership in a fuzzy set. And the second is how do you evaluate the truth value of unconditional and unqualified fuzzy propositions. In that case, we build a fuzzy relation using a fuzzy implication, and that models the truth value. And once you know these two categories, the other two categories in which you have a truth qualifier is pretty easy. All you got to do is just apply the truth qualifier S to your uh, uh, value that you would have otherwise had. Okay, so this basically concludes the part on fuzzy propositions, and all this uh, would be enough for you to uh, solve the assignment questions. Now let us come to the last topic of this session, which are linguistic hedges. Now, what is a linguistic hedge? So suppose I say something like this: the room is very warm. Now I could have said warm as well, but I chose to say very warm. So this word very is a hedge, right? So a hedge is basically a word, or it could be a phrase as well, that help us express decisiveness or indecisiveness in a sentence or in a phrase or in concept, right? So if you compare the two sentences, the room is warm and the room is very warm. So the room is very warm is more decisive in the sense that it asserts a more decisive form of the concept warm, right? It's more. tight as a concept. So I hope you get the point. Tight perhaps is not the right word, but it certainly is a more decisive form of the concept warm, right? Similarly, if I say that the shirt is yellow, then it asserts something about the shirt, that it is of color yellow. However, when I say that the shirt is somewhat yellow, then it feels that we have diluted that concept, right? We have made it indecisive. We have made it so the right word would be dilation. And similarly, the room is very warm. So the word very warm, the concept very warm is a concentration. We more concentrate the concept warm to get very warm. Similarly, when you have the concept yellow, when you say somewhat yellow, you actually dilate it. So previously, a color, say a light orange color, would be yellow to probably degree point 0.8 or 0.75, but it would be somewhat yellow to degree point 0.9, right? So the use of the term somewhat in front of the concept yellow dilates it. It makes it more uh, 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 broad, uh, intuitively, like geometrically. So what do I mean by this? So if yellow was a fuzzy set like this, then somewhat yellow would be like this. So you essentially dilate it. Similarly, Fatima is extremely tall. Extremely, again, is a concentrating, it concentrates or it makes the concept tall more decisive, more tight, more concentrates it's basically, right? So that's what hedges are. These are words that expresses indecisiveness or decisiveness in a sentence. And these hedges, when used with vague concepts like warm, yellow, or tall, modifies their meaning, right? And I hope this is pretty obvious, right? What it means to be warm is different from what it means to be very warm, right? And this modification in meaning is captured by appropriately modifying the underlying fuzzy set. So if we know the fuzzy set that corresponds to the vague concept warm, then I can obtain the fuzzy set corresponding to the vague concept very warm by squaring it, right? So a temperature of 30 degrees centigrade, I'll simply write 30, is warm to, I think everyone would agree if I say it's warm to say degree point 0.9, point 0.8, let's say. In Indian context, uh, so maybe zero point 0.7 is better. So in Indian context, a temperature of 30 degrees centigrade is definitely warm. It is warm to zero point 0.7. But is it very warm? You would say no, it's not, right? So when you apply very, you concentrate it, you make that concept more tight. So it would probably be like close to zero point 0.5, right? Or in other words, you could have obtained it by simply squaring zero point 0.7. It would have given you 0.4 now. So in other words, this way of obtaining the membership function of very warm, the concept very warm, using the membership function warm, uh, is in this particular way is meaningful. It's sensible. Similarly, when we use somewhat, we dilate it, right? We make the concept more flexible, more wide, and that can be done. That can be mathematically achieved by taking the square root. So if yellow of a particular color x naught is um, I don't know, zero point 0.8, then it is somewhat yellow to square root of zero point 0.8, right? And this is definitely greater than zero point 0.8, right? Similarly, extremely, now very and extremely, both these hedges tightens or concentrates a concept, but extremely expresses a, a higher extent of concentration in comparison to very, right? This is how we understand this word very and extremely, right? So if you were to order uh, hedges that are concentrative in nature, then extremely would come after warm, right? So I hope this is not something very confusing to you. Extremely, just think about how we use the word extremely and very in our day-to-day conversations. So in this particular case, extremely tall, the fuzzy set corresponding to the concept extremely tall is obtained by cubing the membership function of concept tall, which means that if uh, uh, you had a height, suppose the height of Fatima was 5.5, 5 feet 5 inch, then say she's tall to degree point 0.7, then she's extremely tall to extent zero point 0.7 cube, which is uh, 0.343, right? So she's extremely tall to a far less degree in comparison to the extent that she's tall. So to summarize, hedges are words that enable us to add decisiveness or indecisiveness in a sentence or in a concept or a phrase. Decisiveness meaning that we make the concept more tight, we concentrate that concept, and indecisiveness means that we dilate it, right? We make it more flexible, more wide. And using these hedges modifies the meaning of the concept that we are talking about. And this modification in meaning can be achieved mathematically in this particular manner. Okay. So is this clear? This idea of hedge. Uh, you can unmute and
Yes, sir.
right.
Yes.
And just a point that hedges are different from truth qualifiers, right? Now we are squaring and we are taking square root, which is kind of same as what we did in when we are talking about truth qualifier, fairly, very true, and fairly false, right? So the formula may be the same, but the meaning is different. Truth qualifiers are attached to propositions and they change the truth value of those propositions, right? So truth qualifiers has to do with proposition, hedges have to do with fuzzy sets, right? So maybe I should make this point very clear because versus truth qualifiers. So this has to do with fuzzy sets. This has to do with fuzzy propositions. So John is tall. This is a proposition, and when we say is very true, we are applying a truth qualifier. However, John is very tall. This is an example of linguistic hedge. Truth qualifiers qualify fuzzy propositions. They are applied on fuzzy propositions. Linguistic hedges are applied on concepts, right? So there's a conceptual difference. Formula might be the same, but there's a conceptual difference, and that you must remember. Okay, so I think this is the last question, and we'll do this question and be done with this session. We have a universe from 0 to 50, the closed interval 0, comma 50, and this essentially denotes the temperature measurements of a city in degrees Celsius, right? And we have a fuzzy set over X named cold, and this fuzzy set cold models the wake concept of cold weather, and it is given in this particular manner. Now, we have three symbols W1, W2, and W3. So W1 denotes weather that is too cold. Okay. W2 denotes the weather that is not too cold. And W3 denotes the weather that is not too cold but somewhat cold. So it's kind of like a pleasant weather. Now we are told that model the hedge 2 as a square and somewhat, so this is somewhat, as square root. And we're required to find the membership of 35, 25, and 20 in W1, W2, and W3 respectively. And we're also asked, is W3 normal? So we have a fuzzy set called, right? Now W1 is defined as 2 cold. So when we applied 2, what did we did? What did we do? We made that concept more tight. We uh, made it more we concentrated it. I'm not sure if that's the right word, but we made it more tight, right? We added decisiveness. And how do we compute the membership of this concept 2 code, which is being denoted by W1? We do that using by applying the square function on the fuzzy set of cold weather. So weather that is not too cold, which is basically being denoted by W1, it is modeled, it's basically a fuzzy set over X, and the membership of that fuzzy set W1 is obtained by squaring the membership of a membership function of the membership function cold, right? Which is basically the fuzzy set that models the wake concept of cold weather, right? So I hope this makes sense. When we apply the hedged T double O, we make the concept more tight. We add decisiveness to it. We concentrate it, and that leads to a change in meaning. And that change in meaning is mathematically achieved like this. Similarly, we have not too cold. Now, this is an interesting case because we have a hedge too cold, we have a hedge too, and we also have this word not, right? Now, this word not expresses some kind of negation, right? I hope that is clear. But what exactly is being negated here? Is the concept too cold being negated, or the hedge too is being negated? It's not clear, right? And this is one of those examples where uh, uh, where things are not very clear. In fact, linguists, people who study language, often talk about this. So if you take a course in linguistics, and there's a section in linguistics called negatives, like so words like not is an example of a negative word, and how negative word behave in situations where you have a hedges or where you have adverbs and adjectives is a very interesting field of research, right? So again, we are students of math. We don't not student of linguistics. So we will abide by this particular interpretation. So not too cold for us would mean that too cold, the concept too cold is being negated. Okay. And not the hedge too is being negated. Okay. So I hope you sort of recognize this nuance here that the word not expresses some kind of negation, and it is not very clear what exactly is being negated. And therefore, as a convention, we will always assume that two negates whatever concept comes after it and not the hedge itself. So, anyways, so W2 would be not, and we already know the membership function of two code, right? So basically, not too cold, we are interpreting as not and too cold. And too cold is basically W1, and then we have a not. So we basically have this, right? And then we will simply perform the complementation, right? And we know that this is basically okay. Now, lastly, we have W3, which denotes weather that is not too cold but somewhat cold. So not too cold but somewhat. But here, I hope it is clear that it's basically and in disguise. Not too cold, we already know how to compute the membership function of not too cold. This is nothing but W2 and somewhat cold. Now, the head somewhat dilates the concept cold, right? It sort of makes it more wide, uh, uh, more wide, dilates it. And how do we obtain the membership of somewhat cold? So the question already tells us that you need to model somewhat using the square root function. So basically, this would be square root of the membership function of cold. Therefore, the membership function of W3, which is basically not too cold but somewhat cold, or in other words, not too cold and somewhat cold, would be, so we have an and here. Therefore, we will take union. We will take the standard union because nothing else is specified. So minimum, not too cold, somewhat cold. And this is basically W2. And we know that the membership of W2 looks like this. And somewhat cold looks like this. So this is how the membership of W3, which is basically the fuzzy set corresponding to weather that is not too cold but somewhat cold, looks like. And we already know the membership function of cold, and therefore you can compute all these three values. So let us do that. So W1 35. So this is cold 35 square. And what would be cold 35? 0 square, because for x greater than 0, mu cold of x is basically 0. So this is 0. 25. So this is so 30 minus 25 by 10 square. In other words, 5 by 10, 1 by 4, so 3 by 4. Similarly, 20 is minimum. 1 minus mu cold of 15 square. So mu cold of 15 would be 1, right? Because for any x less than equal to 20, for any temperature x less than equal to 20 degrees centigrade, it belongs to the fuzzy set cold with membership 1. So this becomes 1 under root 1. So this is 1. Now, is W3 normal? Is the last question we need to answer. So let us plot everything up, right? So this is how the membership function of fuzzy set code looks like. Till 20, you have 1. Between 20 and 30, you decrease according to the rule 30 minus x by 10. And beyond 30, you have 0. Now, let us draw the membership function of fuzzy set W1, which is too cold. And we already know that it is basically the square of the membership function of cold. So this is how cold looks like. And when you square it, when you square a straight line, you essentially get a parabola. And this parabola is essentially this what green line indicates. So this is the membership function of too cold. Now, not too cold. So not too cold is obtained by 1 minus 2 cold. Now 2 cold looks like this. So when you take the negative, you will have this. I should draw a better picture. And then you are adding 1 to it, right? So therefore you end up getting something like this. So this is not 2 cold. Now finally, let us draw the membership function of W3, which is the fuzzy set corresponding to the wake concept, not too cold, but somewhat cold. Now somewhat cold looks like this. So remember, somewhat cold is square root of mu cold of x. So this is how it looks like, the black curve, right? And this is somewhat cold, black curve, and this purple curve is basically not too cold. And W3 is not too cold, but somewhat cold. That is not too cold and somewhat cold. So we basically need to take the minimum of the purple curve and the black curve. So we'll have something like this. In other words, we'll have something like this. And it is very clear that mu of Wx3 is less than 1, right? So what this value is, I think, so suppose this value is, I don't know, like alpha. So it is less than equal to alpha for some alpha less than 1, right? So you can compute this alpha itself. So take that as an homework. So the bottom line is key W3 is not normal because it never achieves the membership value 1. So to go back to our question, is W3 normal? No. What is the membership of 35 in W1? It's 0. What is the membership of 25 in W2? It's 3 by 4. And what is the membership of 20 in W3? It's 1. Okay. So I hope you got a sense of how to deal with propositions wherein you have linguistic hedges. So this is the last question. It combines both the concept of hedge and the concept of truth qualifier. So we have a proposition. A car traveling at 100 kilometers per hour is very fast is fairly true. Very fast. Fast, again, it's a fuzzy set. It's a fast is a vague concept, right? And it is modeled by a fuzzy set. And we are applying very to it. So therefore, this is a hedge. And is fairly true. It's a truth qualified. Now notice that we could have had very true as well here. And therefore, you would have the word very here and here as well. But you should remember that there is a conceptual difference. Truth qualifier applies to propositions, hedges apply to fuzzy sets. Okay. So we need to, we have a universe 40 to 140, and it represents the speed of a car in kilometer per hour on a highway. And the fuzzy set fast, modeling the wake concept fast speed is given like this. Uh, so maybe the universe should be 0 to 140, right? Because starting the universe at 40 does not make a sense, does not make a lot of sense. So maybe 40. And I did not thought of an appropriate membership function beforehand. So I'm doing this on the fly. So maybe 25 and greater than equal to 100 is 1. And between 0 and 1, right? So 25 to 100, so 1. So x minus 25 by 75. So our membership function fast looks like this. Till 25, it is 0. From 25 to 70, it gradually increases and then it becomes 1. Okay. Now, what would be the truth value of this proposition? A car at 10 kilometer is very fast. So very fast concept has a membership function fast x square, right? Now suppose we only had the proposition. So the proposition that we had was a car traveling at 100 kilometer per hour is very fast. Then what would have been the truth value of that proposition? It would have been um, speed is 100 kilometer per hour. So the truth value of the proposition P, suppose this is the proposition P, would have been very fast 100. That's it. But we also have a truth qualifier fairly true. So we need to apply it as well. Fairly true. We know that fairly true is modeled as the square root function. So this would be but very fast, as we just saw, is square. So ultimately you end up getting nothing but fast, right? And what is the membership function of 100? What is the membership of the speed measurement 100 kilometer per hour in the fuzzy set fast? It's 1, right? So let the option D be 1. So option D is correct, right? So this question combined both the concept of linguistic hedge and a truth qualifier, right? And this is how we compute the truth value of the proposition. So if we did not had the truth qualifier fairly true, the truth value of proposition P would have been this thing: the membership of 100 kilometer per hour in the fuzzy set very fast. But since we had fairly true truth qualifier, we had to apply it, and applying it would essentially mean taking the square root. So we'll get square root of membership of 100 in fuzzy set very fast. Now, the membership of very fast is obtained by squaring the membership function of fast. And when you take the square root, you ultimately end up getting this fast itself. And therefore you get 1, right? So was this question clear?
Yes, sir. But we have to frame this membership function, sir.
Right. So this should have been given in the question itself, but I forgot to write that. So I invented one right now.
That's okay. But it's understandable, sir. If this membership function is given, means remaining and all, we can able to understand.
Yeah. Once you know the membership function fast, you can compute very fast, and then you can compute the truth value of this proposition.
Yes.
Yeah. Jaya, do you have any questions? Uh, do you have any questions, Jaya? Okay, so in that case, we'll conclude the session. Um, Thank you for joining.
Thank you, sir. Thank you.